Okay. So what is in this case, all we need to do is add in the values, right, to the formula. And again, one thing that you should sort of kind of get a feel for is making sure that you can check these things so that you can be fairly certain that your answers are correct. If I have negative 11 plus 3, y plus 3, 1,000 is 10 to the third, right? Yeah. So negative 8, and then add 24, so that's going to be 10 to the 16th, divided by, and million is 10 to the 6th, and that's going to, multiplying that number by 2 is going to give me 10 to the 7th, so 10 to the 14th, 10 to the 16th divided by 10 to the 14th is going to give me 10 to the 2nd, so hundreds. So thousands is pretty close to hundreds. You've got a pretty good idea that your answer is close. Okay. So make sure you understand the law of universal gravitation describes a force of attraction. Both gravitational bodies feel the same force in opposite directions, much the same way that the force of tension is the same at both ends of a rope. Okay, and that's difficult for us to understand. If I've got the moon and I've got the Earth, you would think that the force of attraction of the Earth on the moon is going to be much greater than the force of attraction of the moon on the Earth. Okay, it's not that way. If it was that way, then the moon would be accelerating rapidly towards the Earth, and that doesn't happen, right? They stay the same distance apart. One is not accelerating related to the other, at least in a distance term, although the Earth is certainly accelerating the moon towards it. That's the centripetal acceleration that you're talking about there. The moon would want to be there, but instead it's there, right? But as far as it actually getting closer to the Earth, it's not accelerating in that way towards the Earth. And so the forces are balanced, and well, you can think of it in that way. And that force that both of them feel is the force due to the law of gravity. And the thing that's different is that force is going to have a much greater effect on the smaller moon than it is on the Earth, right? That spacecraft as well, the force of gravity between these two things was 4,900 newtons, we said. So both of these feel that force of 4,900 newtons. It's just that the 4,900 newtons affects the spaceship a lot more than it does the Earth, right? It's not going to pull the Earth towards the spaceship. It's going to pull the spaceship towards the Earth. Okay? Now, force equals mass times acceleration is not the same thing. This tells us how any object accelerates due to any type of force. This is not the same thing as Fg equals gmm over r squared. Okay, so anyway, you would be given all of these values. You would be given, if you needed it, the mass of the Earth. You would be given the radius of the Earth. You would be given the gravitational constant. You wouldn't be given force equals mg, but you would be given force equals g times mm over r squared. And so let's see if we can determine g using the universal law of gravitation. We know that the force due to gravity now has a second force. We've got mg equal to g m. And a lot of times we'll put me there for the mass of the Earth over r GR squared. And the force due to gravity that we're talking about is at the surface of the Earth. Okay? So both of these formulas give me a mathematical way to identify the force due to gravity. This is the force due to gravity at the surface of the Earth. This is just the force due to gravity in general. Okay? And what do you think the M here is referring to? Is this the mass that's being... Why are you doing this? The third time today it's done that to me. Okay, so is this the mass that's being pulled on, or is this the mass that's doing the pulling? If I'm talking about something at the surface of the Earth, that's the mass of the object being pulled on. So this is also that mass, right? So both of those masses are going to cancel out, okay? And so the acceleration due to gravity is going to equal 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th kilograms. And this is going to be divided by 6,380,000 meters. And the thing that you're going to forget to do most of the time is square that value. Okay, so 6.67 times 10 to the 11th times 5.98 times 10 to the 6. Wow. I get 9.80 meters per second squared. We know that, right? Okay, so the universal law of gravitation gives us the right value if we compare it to what we already know and use for gravity at the surface of the Earth. Okay, so it should make sense then that we can actually use this kind of thinking to figure out what the acceleration due to gravity is at different distances from the Earth. Yeah.
Are we gonna have to memorize the radius of the Earth?
No, I said that you'll get those on the test.
Okay.
If they want you to know that, they'll give that to you.
Okay, good.
They would never ask you to memorize any constant. Okay. Now, determine the mass using the universal law of gravitation. So if the universal law of gravitation is correct, I should be able to figure out what the mass of the Earth is too then, right? So, and once Newton had this, they could figure out what the mass of the Earth is. Can you imagine if somebody came along in 1680 and said, hey, I can tell you what the mass of the Earth is? They'd think you were nuts, wouldn't they?
They find the radius.
That's a good question. If they thought that it was a flat Earth, that would kind of see. That's another thing about flat Earth. The rules of gravity don't work very well if you have a flat Earth.
Does it have a zero gravity flat Earth?
Well, then why are we being held to the Earth?
You're not. Yes, I'm not a flat earther, but it's fun to think about.
Yeah, it is.
They just like to disagree with it. That's the whole point. It's just to disagree with what we're being told.
Yeah.
So if I say GR squared divided by G equals mass of the Earth, right? I'm just rearranging this, equals 9.80 meters per second squared times 6,380,000 squared divided by 6.67 times 10 to the negative 11th. And you know this is going to work, right? So it should give you 5.98 times 10 to the 24th. And you can think about it this way. So this is 6 times 10 to the 6th. So 10 to the 6th, 10 to the 12th, 10 to the 13th, divided by 10 to the negative 11th is going to give you 10 to the negative 24th, right? So you can already, or 10 to the 24th, not 10 to the negative 24th, 10 to the 13th minus negative 11 will give you 24. So.
Yeah, that's what I thought.
Okay, and then we can determine the acceleration due to gravity at different distances from the Earth. So we can just go back up here and say this equals G ME over R squared. The only thing that's going to be different here is what the R squared is. 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th kilograms divided by, and now it's not 6,380,000, it's 6,389,000. Not a big difference, is it? You got to remember to square that. So, so there is a slight difference, isn't there? 9.80 meters per second squared at sea level versus 9.77 meters per second squared at the top of Mount Everest. That's not a difference that you'd be able to feel though. Okay, so if you were 100 kilograms on at sea level, well, you're going to be 100 kilograms on top of Mount Everest too, but that would mean that you would be 980 newtons here and 977 newtons there. That's less than a pound. So you're going to be less than a pound difference. Okay, so another one of the weird science things that kind of confuse people and make them think they thought they knew everything, but now they don't. It's just the way that we think about satellite motion. If you think of a tower reaching hundreds of kilograms above the surface of the Earth, and this would be above where atmospheric particles could slow motion of an object down, because you don't want particles slowing the motion of an object down, and you fired a cannonball at a velocity less than a velocity that might keep it in orbit, you're aware that that cannonball is just going to plummet to the Earth, right? If I fire it a little bit further, it's going to travel further around the surface, right? And if I fire it a little bit faster yet, it's going to keep doing that. But eventually, I'm going to fire it fast enough that as it's falling towards the surface of the Earth, because of the curvature of the Earth, it's going to stay in orbit. Okay? I run out of Earth to actually fall into. I can keep doing this, and I might land here, and then I might land here, and then I might hit this, I might smack that, and finally I'm going to get to a point where I fire it fast enough that as it's falling towards the surface of the Earth, I run out of Earth to fall into, and I run out of tower to fall into, and I get back to the same point here, because as I fall towards the surface of the Earth, I run out of surface of the Earth to fall back into. So when you think about this, you would correctly state the cannonball would travel in a curved path because the force due to gravity would pull it into a circular path. However, because the velocity is not great enough, as the cannonball gets closer and closer to Earth, its velocity becomes greater and greater, and it finally hits the Earth. It experiences a tangential acceleration. Remember, we talked about the fact that it's going to increase in its path around the circle as well as be accelerated in a circle. So it's going to have both tangential and centripetal acceleration. If we launch it with greater and greater speed, cannonball travels further before it hits the ground, but still experiences tangential acceleration, still falls to the ground. We can reach this until we reach a point at which, as the satellite accelerates towards the Earth, it remains the same distance from the Earth because its high velocity keeps it from getting closer to the Earth. Gravity is still pulling it towards the center of the Earth, causing its centripetal acceleration. But at this point, there's no longer any tangential acceleration. And what I want you to see then is that as we fire this cannonball, it wants to go straight, right? It wants to go straight, but the Earth pulls it. It wants to be here, but the Earth pulls it to this point. Okay? It wants to be here, but the Earth pulls it to this point. Right? It accelerates it towards the center. But as it's going around, it's no longer increasing in its velocity around the circle of the path. Okay? It's no longer experiencing tangential acceleration. It's going that same velocity. Okay, so finally we get to a velocity that's fast enough that allows it to stay the same distance above the surface of the Earth. It's still being pulled towards the center of the Earth, but it's going fast enough that it will be able to not fall out of orbit. And we can think about that a lot like we can our vertical loop here sometimes, right? As we think about the object at the height of our vertical loop, it's going fast enough that it's not just dropping off of the, or maybe a roller coaster, right? It's going fast enough that it's not just falling at that point. And so this is kind of like that. But what we want to get to is an expression that talks about the velocity of the satellite at a particular elevation. So knowing that the only force acting on the satellite is gravity, and knowing that it's causing a centripetal acceleration, we can equate the universal law of gravity to the centripetal force formula. And that's what we've done in a lot of other situations too, right? We've said that tension equals mv squared over r. Or we've said that in the banking formula, we said that mg tangent of theta equals mv squared over r, right? So the m's cancel out there. So in all of these circumstances, we're going to find that we can equate the force that's causing the centripetal acceleration. In this case, it's the force due to gravity that's causing the centripetal acceleration, right? We can equate this force to the centripetal force formula. And so if I want to find out what the velocity of a satellite is at a certain radius, I can equate gravity to my centripetal force formula. The mass that's being pulled on cancels out, and then all I need to do is also cancel out the r and the square there, and then I can see that the velocity needs to this whole thing needs to be square rooted. So the velocity of a satellite at a particular radius is going to equal the square root of gravitational constant times the mass of the Earth divided by the radius. And what this tells us is that the velocity needed to maintain an orbit only depends on the radius of the orbit. The velocity needed to maintain an orbit only depends on the radius of an orbit. Okay, it doesn't depend on the mass at all. Okay, so note, if an object attains a higher speed, it will simply go into a higher orbit. Okay, if I go faster, I'll just go into a higher orbit. Although above 40,000 kilometers per hour, it will escape Earth's gravitational pull. Okay? So, see if we can solve this problem. A geosynchronous satellite is one that stays above the same point of the Earth, which is only possible if it's a point above the equator, because the center of the satellite orbit is always at the center of the Earth. It's not possible to have a satellite orbiting above a fixed point on the Earth at any latitude other than 0 degrees. Okay, so if I want to have a satellite that has the same period as the Earth, right? Earth rotates once every 24 hours. The satellite also has to go around once every 24 hours, right? So this spot and the satellite are going to follow each other all the way around the Earth. So that will be at a fixed spot above the Earth. You having trouble staying awake? Here you go.
I'm just shaking my head.
Oh, okay. That's right if you are. I'm pretty boring. Determine the height above the Earth's surface such a satellite must orbit and its speed. What kind of a satellite would we want to always be above the same point above the Earth?
Missile.
A missile satellite?
Yeah.
We don't want it to go anywhere. We just want it to be above the same point.
We need to know where it is so that way we're able to calculate how far and how fast we can launch it.
Okay, well, we should be able to do, well, so is the missile on the satellite?
I don't know.
Oh, okay. How about a weather satellite? Do I want something that's watching the Western Pacific Ocean to be over, or the Eastern Pacific Ocean to be over the Eastern Pacific Ocean the whole time? So weather satellites, we're going to want to have over that. But a lot of our other satellites, we move all over because we want to have them look at different things, right? A lot of our satellites we don't want above a fixed point above the Earth. We want the Earth rotating underneath of it, so we may not have it moving. But anyway, determine the height above the Earth's surface such a satellite must orbit and its speed. Okay, so how am I going to figure that out? Okay, so I'm going to need to know what the radius of the orbit is, right? I want to know what the radius of the orbit is. And I'm going to need to use V equals the square root of G, mass of the Earth, divided by the radius to figure that out. But I have a problem because I've got two variables that I don't know, right? I don't know the velocity and I don't know the radius. So what can I do to help me out here? What can I do to help me out here? Is there something else that I know about the velocity that might help me? Do I know that V equals 2 pi r over the period? Okay, so V equals 2 pi r over the period. And so maybe or I could say that V squared equals 4 pi squared r over, let's see, how did that work? T squared, 4 pi squared r, t squared, equals, and so I'm going to say G me over r, right? Because if I want to get rid of the square root, which I want to get rid of the square root, I'm going to need to square the velocity. And in this case, I don't have the r underneath to cancel that, right? With the and let's just make sure we understand that with the centripetal force, or with the centripetal acceleration, it's v squared over r, right? A equals v squared over r. So when I do that squaring of the v, I end up with 2 pi, I end up with 4 pi squared r squared over t over t squared over r, right? And that r cancels out, so I end up with 4 pi squared r over t. But here I don't have that, so I've got this, okay? And what's that going to do to me? I'm going to have to multiply both sides of the equation by r to get rid of that, so that's going to give me r cubed. Okay, and so now I'm going to have the cube root of r, or r cubed equals t squared g me over 4 pi squared. Okay, so I'm going to have to do some calculations here. What's t? What is t? It's the period, right?
Yeah.
Okay, what's the period of the rotation?
24 hours.
Okay, so I need that in seconds, though, don't I? So 24 times 60 times 60 equals 86,400. So r cubed equals 86,400 squared times 6.67 times 10 to the negative 11th times 5.98 times 10 to the negative, or times 10 to the 24th, not negative 24th, kilograms, divided by 4 pi squared. So okay. I get 4.23 times 10 to the oops, 4.23 times 10 to the 8th, 7th or 8th, 10 to the 7th meters above the surface of the earth, or not above the surface of the earth, but from the center of the earth. And I need to subtract 6.38 times 10 to the 6th meters, because that's the distance between the center of the earth and the earth, surface of the earth. And that gives me 35,870,000 meters, or 35,000 kilometers. 35,870 kilometers. Okay. Is that what you got?
Yeah.
Or are you just saying that? Yeah, what'd you get?
What's the, in between the 86400 and the, what's between the parentheses, like,
Here?
yeah. What's the one before that, like, outside?
86,400 squared,
And then what's after that?
6.67 times 10 to the negative 11.
Okay.
That's the gravitational constant. That's big G. Okay. And then I took the cube root of all of that and got 4.2 times, or so 42,300,000. I subtracted the distance from the center of the Earth to the surface of the Earth. And so should be 35,870 kilometers above the surface of the Earth. Okay, and at that point, at that height, it wants